Here we will solve a least square approximation problem using the QR decomposition. So recall that QR decomposition is when A is equal to QR. And to solve least square problem, you need to find D, which is equal to Q transpose B, where B is the set of data that is given to you at the beginning, so you already know the values. And then you will solve R0x equals D0, where x are the values you are looking for. R0 is the upper triangle matrix, but only with rows that contain non-zero elements, with only rows that have at least one non-zero element. Okay, if R has some rows with values, but then there is one row or maybe two with only zeros, you would cut that row, and so R0 would be given here in this case by it will only contain the rows that have at least one non-zero element. And by D0, basically, remember that D is equal to D0, D1. D0 is if by R you cut the last row, then by D you will also cut the last row. The goal is to have the same number as rows by D0 than by R0. Okay? Remember that. And then you can use, you have a system of linear equation to solve, and then you can solve for x. Okay? Remember that. And so here I will solve this least square approximation problem using QR decomposition. In the last video I used the singular value decomposition, but here I will do it with the QR factorization. So let's say that our matrix is given by our matrix A is given by 0, 1, 1 over square root of 2, 1 over square root of 2, square root of 2, negative 1 over square root of 2. Okay, so I will solve the same problem, but instead of using the singular value decomposition, I will use the QR factorization. Okay. So my goal is to find the QR decomposition. I think I don't even need to find Q, I just need Q transpose. Okay, because I want to find D, which is equal to Q transpose B. And our vector B is given by square root of 2, 1, 1. Okay. And in this problem, my unknown won't be x, but beta. Okay, I will have beta 1 and beta 2, as I did with my problem using the singular value decomposition in the last video. Okay. So, and for the QR decomposition, I will use householder. Okay. You can also do it with the Givens rotation or Gram-Schmidt. I will maybe do a video about it, maybe. Okay. So if I have my matrix, remember that the householder transformation is given by the identity matrix minus 2 times VV transpose. So I will find V1. So I will choose the first column of A. Okay, that will be A1. So first I will find a vector U1 which is equal to A1 minus the length, of A1 times the unit vector E1. Okay, remember that. So A1 is this column vector here, and its length is given. Its length will be given by. So if you calculate it, it will be given by. I will do it. The square root of 1 over the square root of 2 squared plus. Okay, the first on 3 is 0, so I don't need it. So I would get the square root of if I do that, I get 1 over 2 plus 1 over 2, which is 2 over 2, so the square root of 1, so that would give me 1. Okay, it's simple. And so I would get A1 basically minus E1, okay, because the norm is 1, the length is 1. And so if I do that, I will get the vector. So let me maybe write it. 0, 1 over square root of 2. So that's a 1 here. Minus the length, which is 1. Minus 1, 0, 0. And so I should get negative 1, 1 over square root of 2, 1 over square root of 2. Okay? That's a 1 here. Okay. And so V, so that's my vector U1, and now to get V, I just divide U by its length. So V1 is U1 over its length. And so I should get I should get 1 over square root of 2 times negative 1, 1 over square root of 2, 1 over square root of 2. Okay? And so that's V1. So now I can find the first Householder transformation, which will be given by the identity matrix minus 2 times V1 transpose. Okay. So if I calculate that, I will get the identity matrix minus 1 minus 1 over square root of 2, that's 1 over negative 1 over square root of 2, negative 1 over square root of 2, negative 1 over square root of 2, 1 over 2, 1 over 2, 1 over 2, 1 over 2, negative 1 over square root of 2. Okay. Okay, so the 2 here should be here. And by the way, I think that it's a symmetric matrix. Or is it? Isn't it? Yeah, I think it's symmetric, by the way. We don't need it, but yeah, it's symmetric. So that helps. Or is it always symmetric? I don't know, but never mind. So if you compute that, you should get 0, 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, 1 over 2, negative 1 over 2, 1 over square root of 2, negative 1 over 2, 1 over 2. It's a 2 here. Okay, so that's H1. Now we will apply it to A. Okay. So that's just computation. Maybe I will do the calculation. Sorry. Is it the same? Should be. Okay, times A, which is 0, 1, 1 over square root of 2, 1 over square root of 2, 1 over square root of 2, negative 1 over square root of 2. Okay? And so if you calculate that, it's matrix multiplication, you should get 1, 0, 0, 0, square root of 2, 0. And by the way, you can see that so we get our two 0 elements here, but we also get a 0 element here. It wasn't foreseen, but yeah. And so we don't need to do a second Hausdorff transformation. Here we just were lucky enough to get the 0 in the second column too. Okay, and so this is already equal to our upper triangular matrix. Okay. So we only need one transformation here. That's good. And so we can write that H1A is equal to R. Now we see that R has a row that contains only zeros. So we can cut it because basically it doesn't give us more information. Remember, our goal is then at the very end we will do R0x is equal to D0. Okay, but so you have your vector x, let's say x1 and x2. Let's say we take our matrix R. Let's take our matrix R. If we multiply it by x1 and x2 and to get d0, you will see that we will get one vector in 3 dimensions, but the last dimension will be 0. but our goal is to find x1 and x2. But the third equation doesn't really help us. Okay, we will get 0 times x1 plus 0 times x2 is equal to the third row of d0. But that doesn't really help us to find x1 and x2. That's because of that we cut the rows with the zeros. So you see what I mean? It doesn't help us to find x1 and x2. Okay, so I cut the last row. Now to find d, I know that it's equal to q transpose b. Okay, and remember that a is equal to qr, so q transpose a is equal to r, and so q transpose is already equal to h1. Okay, q would be equal to h1 transpose, but we don't need it. And so we already know our q transpose. It's just h1, which is this matrix here. Okay. And so we can find d. Remember that b is square root of 2, 1, 1. And so if we compute, we will get that d is equal to d will also be equal to square root of 2, 1, 1. Okay, you will also get that. You can do the computation, you will get that. Now d0 will be equal to square root of 2 and 1. Okay, remember we cut the last row because we cut it by r. And now we can solve the system. So r0x is equal to d0. By the way, I said that I won't use x but beta at the beginning of the video. Sorry, there should be a beta here, and here there should be a beta. I just said that I won't use x but beta as a variable. Okay, it doesn't change something, but in the last video I used beta, so I wanted to use beta here too. Okay, and so we know r0, which is 1, 0, 0 square root of 2. We know d0, should be a 1 here, and so we will get that 1, 0, 0 square root of 2 times beta 1, beta 2 is equal to square root of 2, 1. And so you can put that in, you can solve the system. You will get that beta 1 is equal to square root of 2. You will get, if you multiply that matrix, you will get that square root of 2 times beta 2 is equal to 1. So beta 2 is equal to 1 over square root of 2, which is what we get as results in our last video too. So yeah, so if you get the same result, that means I did no mistake. And so yeah, I hope this video helped you. So just remember, you can use the QR factorization to solve least square problems. You need to find d, which is equal to q transpose b. B are the set of values that are given at the beginning, and then you solve r0 beta or r0x is equal to d0. D0, okay. And so r0, by R0 you only take the rows that have at least one non-zero element. Otherwise, that they don't help us. They give you no more information to find the betas or the x's. And you cut the same number of rows by d to get d0, and then you solve your least square problem. So yeah, thanks for watching.